address questions about morphological and functional diversification. Thanks for coming. So I'm going to be talking about performance surfaces. I'm going to start by talking about what a performance surface is. So performance surface is something that you all most likely either have or can derive from some of your organismal data. You've got some measure of an organismal phenotype. I'm interested in turtle shells, aren't we all? So I'm going to be looking at a simple measure of turtle shell shape, just a height to width ratio. Really high shells over here, ridiculously low shells either over here, normal looking shells in the middle. And this measure of the phenotype has some relationship with performance in some organismal function. So let's first look at one important function for turtles. This is being able to flip right side up after you've been turned over on your back. And it turns out that shell shape probably has a big influence on how easy it is for turtles to do so. So the performance surface for riding ability in these turtles might look something like this. It seems like the peak is probably somewhere around a 1-to-1 ratio, maybe a little bit higher. It gets more difficult as the shells get taller because you end up on your side, hard to get right side up. It gets more difficult as the shells get flatter too because it's hard to get past that edge of the shell before you can get right side up again. It's rare that structures have only one function, and the turtle shell is no exception. So here's another potential performance surface for turtle shell shape. This is hydrodynamic performance, swimming ability, not generating a lot of drag when you're moving through water. So over here, flatter is better. The flatter you are, the less frontal area you're going to get to the water, the less drag you're going to generate, all else being equal. So we've got, for this particular structure, a couple of performance surfaces, a couple of relationships between some aspect of the phenotype and performance in these functions. These can be two-dimensional, too. This one's a little bit more complicated. Two principal components for an analysis of shape on 255 extant hard-shell turtle species. Once again, we're going to be looking at hydrodynamics right here. So I'm going to be approximating the performance of moving through the water with the frontal area of the turtle shell, so the area that you would see if the turtle was coming right at you. For this, low numbers are, let's see, so good performance over here, bad performance up here. High numbers are bad for this particular measure. And then here's another one. Here's another measure of shape that can approximate riding ability. So this is the R index. That's just the height to width ratio that I showed you all earlier. And here, low numbers are bad for riding. High numbers are very good. So you've got these surfaces in two dimensions that show you how performance varies with shape. And these can be multidimensional too. It just gets harder to show them after you go past 2 dimensions. So it's easy to predict organismal distributions if you only have one performance surface. If riding ability is the only factor that's influencing shell shape, no other functions, no trade-offs, nothing else, then it's pretty intuitive that turtles would evolve to the optimum shell shape for that performance. So if you're only concerned about riding ability with your shell, nothing else, you're going to have a pretty high height to width ratio, maybe end up looking like this plowshare tortoise here. On the other hand, if hydrodynamic performance is the only factor influencing turtle shell shape, nothing else, then you're going to be as flat as possible and probably end up looking like a sort of a soft shell turtle. But we know that that's unrealistic. We know that structures usually perform more than one function. There's almost never selection on just one function for an organismal structure. So how can we combine these performance surfaces in order to understand where we expect turtles to be along this one particular axis of shape? Well, it's hard if we don't have any sense of how important these functions are for the turtle, how ecology influences this. We could have shapes that are at either the optima or anywhere in between for like an aquatic turtle for whom hydrodynamics and riding ability can both be important. But we can say one thing. we can say that we don't expect any turtles in this gray area right here. And why is that? Well, that's because by evolving a lower height to width ratio, you get improvement in performance for both of those functions. So there's no reason for turtles to stay there. They should evolve at least towards this point, if not further. Okay? And that is in fact what we see for a variety of turtles, both aquatic, for whom both these functions would be appropriate, and some other terrestrial ones as well. Okay. You can do this same thing in multiple dimensions, although it starts to get more complicated. So here, once again, is this two-dimensional performance surface for hydrodynamic performance, for swimming ability. I've already shown you all this one. I'm going to be looking at a different one now to talk about these trade-offs. So this is a performance surface for shell strength. We evaluated shell strength using finite element modeling. I can't talk about it a lot here. I'm happy to talk to you after this particular session about what we did with the finite element methods. But we measured how much stress is generated in turtle shells of a variety of different shapes throughout this morphospace. We took the average stress for 12 load cases, 12 different sort of biting scenarios. Here, higher numbers are bad. Stress is what makes turtle shells break, so the higher it is, the worse it is. So we've got both of these performance surfaces lined up side by side. Hydrodynamics right here, strength over here. Usually, for these surfaces, evolution in one direction from a certain spot is going to require a trade-off. So here, starting here, evolving a higher PC1 score, well, you're going to get less stress, and that's good. That's a stronger shell. But you're going to get a higher frontal area, so that's going to be a harder shell to swim with. So, that requires a trade-off that may or may not be beneficial for a given turtle species. However, this isn't the case in every part of these performance surfaces. Down here, for example, you can start off with a very low PC2 score and evolve a higher score, and that gives you both a lower frontal area and less stress. Okay, so this is another one of these areas that we don't expect turtle shells to be if they're evolving in response to selection for hydrodynamic performance and strength, because they can move in one direction from one spot and get better performance for both functions. And you can map out the points in space where this is possible and mark a boundary between the places where you can get improved for performance by evolution in one direction and the places that you can't. You can mark out this line right here that separates regions that you can move away from and get increased performance from regions where evolution in any direction is going to require trade-offs. Okay, so this line right here is called a Pareto front. So let's expand this a little bit. So once again, the Pareto front for hydrodynamics and strength. Thanks, by the way, to some of my undergraduate research students who put together the algorithms to actually make plotting these possible. Now here, just like with the one-dimensional data, we don't expect any turtles in this area. Movement in at least one direction out of this area gives you improved performance for both functions, so no turtles should stick around there. We do expect to see turtles, or at least aquatic turtles, turtles for whom both hydrodynamics and strength are important, only in this area right here. And that is what we see. Some of them come close, but the only turtles that cross this line are terrestrial turtles, for whom hydrodynamics aren't important. Okay, so we can do this at least. We can mark off areas where we don't expect any organisms to be, and if they ended up crossing this line, say, we might start to question the importance of both of these functions for those groups. So at least this gives us some negative predictions. We can predict where our organisms won't be based on these performance services. However, one wants to go farther than that. It seems like there should be more information that you can get out of this. And you can if you're willing to make some assumptions. For example, if you're willing to assume that performance is going to be proportional to fitness for these functions, and you're willing to give them different weights based on how important they are for fitness, then you can start adding these performance surfaces to get adaptive surfaces, adaptive landscapes. So right now, let's just assume that both hydrodynamics and riding are equally important for these species. We can simply add performance in both of those, scaling both of them to sort of a 1 right here, to get this nice adaptive surface, and we'll predict that for a turtle, for whom strength and hydrodynamics are equally important, it should end up around there. Okay? Anywhere else would give you a disproportionate decrease in one of those functions relative to the gains that you'd make in the other. And it's closer to the peak for riding ability because that one's got a steeper slope in that area. Now you may have some ecological information about your taxa. Maybe you think, no, writing isn't as important. Maybe it's only about 90% as important in hydrodynamics. So you can weight it at 0.9 relative to hydrodynamics, and you get a little shift in the peak of this new adaptive surface. Maybe writing ability is only half as important hydrodynamics as hydrodynamics. Maybe these turtles don't come onto land that often. You get another shift of the peak in this adaptive relationship right here. And you can keep doing this, changing the relative importance of one of the functions compared to the other, decreasing the importance of writing ability, getting a new peak, until finally, writing ability is completely unimportant, and the peak of our adaptive surface matches up entirely with the peak of the performance surface for hydrodynamics. Once again, this is something that you can do in multiple dimensions. Oh, sorry. You can also run this process in reverse, too. You can start off with a turtle that has a certain phenotype. So you've got a turtle that's got this particular height-to-width ratio right here, and you can ask what relative weighting of these performance surfaces would give you a peak right here. So assuming, you're willing to assume that this animal is at its peak for compromising hydrodynamics and writing, you can ask what the relative importance of those performance surfaces would be. And here it turns out that, for this spot right here, that implies that writing ability is only 65% as important as hydrodynamics for this term. Okay, so it was this insight, this inspiration, that was the impetus for a method that we developed, me and my colleagues, in a paper in the Journal of Vertebrate Paleontology, for extending this idea, making it more quantitative, and putting it in multiple dimensions. So we developed a model, by which I mean Dave Pauly mostly developed a model, but the rest of us helped do. We started off with a set of performance surfaces. This is not for all turtles, this is just for emided turtles now. Once again, it's performance surfaces for functions that you all are familiar with. So here's shell strength, good shapes up here, bad shapes down here. And for hydrodynamics, good shapes down here, bad shapes up here. And you can add these surfaces together, weighting one of them relative to the other by different amounts, to predict where the optimum shapes or shapes would be in this space. So, if hydrodynamics really aren't that important, the peak falls really close to the maximum performance for shell strength. If hydrodynamics are not very important, are more important than strength, then you get a peak much closer to the peak for hydrodynamics. And in fact, all of the peaks for any combination of weights of these variables are going to fall along that line there. That doesn't have to be the case. It doesn't have to be a line. It doesn't have to be a straight line. Actually, this line isn't perfectly straight. But we expect all turtles, whatever the relative importance of hydrodynamics and strength are, to fall along that line. So of course they don't, but you can run a perpendicular to that line from where your particular taxon of interest is. So like this big A right here, that's a Picta, a nice painted turtle. Run your perpendicular. Developed a likelihood function to determine what the most likely weighting of performance of hydrodynamics relative to strength would be. So for this taxon right here, hydrodynamics are only 84% as important as strength. And we did this for all of the turtles in this analysis, getting a relative weighting of hydrodynamics compared to strength. And you can use this to ask a number of questions like, for example, do aquatic taxa have shell shapes consistent with a higher relative importance for hydrodynamics than terrestrial taxa do? So the weightings are right here, relatively unimportant. Hydrodynamic weighting is like blues and purples. Hydrodynamics are really important, it's in reds and yellows. And you can see that for many of these terrestrial taxa, hydrodynamics are relatively important, but not all. And for many of the aquatic taxa, hydrodynamics are quite important, but for not all of them. So here's a turtle right here for whom hydrodynamics seem relatively unimportant. Maybe we have some ecological information about that taxon that can explain why it seems to be emphasizing strength a lot more. Okay, so those are my two methods for combining performance surfaces, using them to mark out regions where you don't expect any taxa, and using them to estimate the relative importance of different functional factors in organismal evolution. If you are interested in turtles, I've also got 3 students here who are giving poster presentations on Monday, and now I will model good behavior and switch over to the next speaker. Thank you.